Okay, so we started a discussion on light and visible spectrum. We were on page 104, about to address on your own 3.4. Okay, so on your own 3.4. Let's go ahead and I'm going to do as I do sometimes, have you actually work it but be ahead of me a little bit, get a start on it, and we'll go through it together. So on your own 3.4, page 104 says, what color is light that has a frequency of 6.4 times 10 to the 14th hertz? What color light is it if it has a frequency of 6.4 times 10 to the 14th hertz? What's going to be what's our strategy going to be? How are we going to determine the color of the light? What is the only way you know so far to determine the color of the light? If you flip back to page 100, you have a chart there that has the different colors and the corresponding what? Look below that chart. What does it show? A corresponding, see where it says 700, 650, 600, 550. Those are all what units? Nanometers, right? So what are they measuring there? 650 nanometers, what is that? Or 550 nanometers. What does that number represent? Okay, pardon? The wavelength, okay, good. The wavelength of that wave. So in order to determine the color, the only thing we know to do at this point is to look at the chart and compare the wavelength of the light to a wavelength on the chart so we can approximate the color. Are you given wavelength? No, you have frequency, right? So somehow we've got to move from frequency to wavelength. And how do you propose we do that? Good idea. We'll use the first formula that we learned for the module, one of two, that frequency is equal to the speed of light divided by the wavelength. But we need to solve for the wavelength. So to solve for the wavelength, we need to rearrange the formula, not solving for frequency, but solving for wavelength. And that's what it looks like as we rearrange it. The wavelength is equal to the speed of light divided by the frequency. Remember, these two things are inversely proportional, meaning when one goes up, the other one goes down. All the time. So wavelength goes up, frequency goes down. Frequency goes up, wavelength goes down. Why? Because they're related by virtue of a constant, meaning the product of the two things. Wavelength times frequency always equals the speed of light. So if one goes up, the other one has to go down to keep it constant. Okay, so now we have a formula with the wavelength to find the wavelength given the frequency, because c is a constant, remember? So we have it in two forms, metric or imperial, so we can do it in meters or feet. But it makes sense for us to stay metric, right? Because our graph is going to be nanometers, and we don't have to convert from feet to meters. So we'll keep it in terms of meters. So we have to write the formula out in some way to solve for the wavelength in meters. So if wavelength is equal to the speed of light divided by the frequency, let's just plug in what we know. We know that the speed of light is 3.0 times 10 to the 8 meters per second. Now yesterday on the slides, I had a typo on the slides yesterday, and I made the typo once, and because I reused the slides several times, the typo got carried all down the whole page. So one of your classmates came up to me afterward and said, why did you use 3.08 times 10 to the 8th? That was a typo. It's 3.0 times 10 to the 8th. Okay. So 3.0 times 10 to the 8th meters per second is the speed of light. We're going to divide that by the frequency, and we've been given the frequency of 6.4 times 10 to the 14th hertz. So we just have to do the math. What is 3.0 times 10 to the 8th divided by 6.4 times 10 to the 14th? Let's estimate it. For those of you that are already punching away in the calculator, that's cool. Those of us that want to just use the old slide rule method, or even better, just figure it out in your head. Let's look at it real quick. We've got 3, let's look at the coefficients. 3 divided by 6.5. About what is that number going to be? 3 divided by 6 would be a half, right? So it can be a little bit less than a half. Okay. a little bit less than half. So let's just throw a number out there. Make it easy and go 0.4. That's a little bit less than half, right? 0.4 is a little bit less than 0.5. So 0.4 times 10 to what? We've got 8 divided by 8 times 10 to the 8th divided by times 10 to the 14th. Remember, when you divide, what the process there is you subtract the exponents. So 8 minus 14 gives us a negative 6. So 0.4 times 10 to the negative 6, that's really going to be 0.5 times 10 to the negative 7. Right? Let's see, what did I have? 4.7 times 10 to the negative 7. Okay, so it's in the ballpark, right? If I estimated 4 times 10 to the negative 7, got 4.7, yeah, okay, that's about what I expected it to be. So I'll know that I didn't make a mistake with my thumbs when I was punching it in. Hopefully you can see now that 4.7 times 10 to the negative 7th meters, my scale here is in nanometers, right? So if I can rewrite that times 10 to the negative 9th, then I can just say times 10 to the negative 9th meters is the same as a nanometer. Did everybody follow that? If I can change this from being something times 10 to the negative 7th, if I can change it to something times 10 to the negative 9th, well, times 10 to the negative 9th meters is a nanometer. So I can just change times 10 to the negative 9th meters into nm for nanometer. So I need to make this number smaller 2 places, so I make that number look larger 2 places. See? So that's the way I think of it. Technically, sig figs and everything, this is not absolutely technically correct, okay? But just work with me on that, because we would never write 4.7 times 10, or 470 times 10 to the negative 9th, right? Where's the decimal point in that? That's technically not right. But because it's in this form, I can think of it as 470 times, well, 10 to the negative 9th meters is the same as a nanometer. So 4.7 times 10 to the negative 7th meters is equal to 470 nanometers. Now I go back to page 100, look at my spectrum there. 470 nanometers. Where's 470 at? 470 lands within the range between what 2 numbers? 450 and 5, which on this grid is indicated, the color is blue, right? So the color of light is blue. Because a frequency of 6.4 times 10 to the 14th hertz means that that waveform has a wavelength of 470 nanometers, and according to the chart, 470 nanometers is a blue light. So we see blue because of the wavelength of that light coming in, which is related to the frequency of that light coming in as well. Okay? Similar problem is 3.5. 3.5 says if red light has a wavelength from 7 times 10 to the second nanometers to 6.5 times 10 to the second nanometers, what is the frequency range of the red light? So now we're just working it the other way around, right? Rather than being given a wavelength, we've been given, rather than looking for the wavelength, we've been given wavelengths, and now we need to solve for frequencies. This is actually 2 problems. We need to convert this wavelength into frequency and this wavelength into frequency to get the frequency range. The chart we have on page 100 gives us the wavelength range. So every specific wavelength has a corresponding specific frequency. What are they? We're just going to use the same formula that the frequency is equal to the speed of light divided by the wavelength for both of those endpoints. So for the first one, the speed of light is 3.0 times 10 to the 8th meters per second, and we're going to divide that by the wavelength of the first endpoint, 7.00 times 10 to the second nanometers, which is 7.00 times 10 to the negative 7th meters, right? Divide that out, we get meters per second divided by meters gives us a 1 per second, which we know is a hertz. And so it's 4.3 times 10 to the 14th. And the other frequency, same thing, using 6.5 times 10 to the negative 7th meters. Maybe this isn't clear how we got 10 to the negative 7th meters from 10 to the second nanometers. You could, in your mind, rationalize it or think of it this way. 6.50 times 10 to the second times 10 to the negative 9th meters, right? Because 10 to the second, that takes care of this, and then this is a 1 times 10 to the negative 9th. positive 2, positive times 10 to the second, times 1 times 10 to the negative 9th. When you multiply, you add the exponents, right? So 2 plus a negative 9 gives you a negative 7. Okay? So again, estimating here, we're kind of where we were before, right? Let's just estimate this. We have a 3 divided by a 6.5, something divided by something a little bit more than twice its size. So we're going to have something around 4 again. Let's just use 4 again. And we've got times 10 to the 8th divided by a negative 7, which means we're going to subtract the negative, same as adding, so it's times 10 to the 15th. 0.4 times 10 to the 15th. The same thing is about 4 times 10 to the 14th. So 4.6. You know, an exponent should be pretty close, or right here. So 4.3 times 10 to the 14th and 4.6 times 10 to the 14th is the range. So if red light has a wavelength range of 7.00 times 10 to the second nanometers to 6.5 times 10 to the second nanometers, another way of saying that is that red light has a frequency range of 4.3 times 10 to the 14th hertz and 4.6 times 10 to the 14th hertz. It would be a different chart. It would be looking at page 100, and every one of those nanometer marks would have a frequency mark underneath it. And as you look at the wavelength, as the wavelength gets larger, the frequencies would get smaller. See? Look up here. This wavelength is larger than this one. This frequency here is smaller than this one. So as the wavelength gets larger, the frequency gets smaller. Got some very excited young people. So those are on your owns. 3.4 and 3.5. How those are worked out are in your text. So if this didn't make sense, if it was too fast for you, you can review it in the text. You can obviously go on YouTube and watch this video again to walk through this process. And if my estimations and all this stuff is kind of confusing to you, if you were able to convert from nanometers to meters, punching it in your calculator with the calculators you're allowed to use in here, you should get the right answers. Just understand process. Be able to set it up. Okay. We're going to go back to our discussion on properties of light. We're technically in this section now on the electromagnetic spectrum and talking about frequency and wavelength. Remember we mentioned yesterday that frequency and wavelength are inversely proportional. That's that whole idea. If one goes up, the other goes down. They're always, the product of the two multiplied together is always going to be constant. But this inverse proportionality means one goes up, the other goes down. We don't have situations where both would go up, because if they both went up, what we're doing is increasing the speed of light. And if they both went down, we're decreasing the speed of light. When they oscillate proportionally, inversely, the product is remaining the same, the speed of light. So frequency and wavelength are inversely proportional. Large frequency, small wavelength, small frequency, large wavelength. Okay. That is the inverse proportionality. I've got another chart that might show this a little more clearly, but those are the principles right now that you need to remember. Frequency and wavelength are inversely proportional. Now, we showed this graph the other day, the visible spectrum. If you were to take this and compare it to the chart in your book, I want you to realize that they're inverses of each other. I mean, if you looked at page 105, figure 311, it shows the electromagnetic spectrum, and it shows from gamma rays on the left to AM radio on the right. Okay. So from left to right in your book is showing increasing wavelength. This chart here goes from AM radio on the left and gammas on the right, and what it's based upon is increasing frequency, right? And since they're inversely proportional, they're both correct. They're just coming at it from a different perspective. One is showing increase left to right. wavelength, the other one increase left to right of frequency. So don't let that confuse you. The main thing you want to see from this is that what we call visible light is part of the entire electromagnetic spectrum. Okay? And don't let it confuse you in the book if they say light energy or electromagnetic energy. Radio waves, infrared rays, visible spectrum, ultraviolet, X-rays, gamma rays, they're all part of the electromagnetic spectrum. We only can see a portion of that. With the receptive tools that God has given us, we can only see a portion of it. So just to make you aware, if you look at the book and it shows one direction, up here it shows another direction, they're not wrong. They're just looking at the same thing, one based on wavelength, one based on frequency. It's the same thing. But that visible section in the middle is still the key point for us to understand. Now, the next thing we're going to talk about is energy. It's because energy waves, or energy that gets communicated by the wave, or that impacts you from the wave. A principle you need to know here is that frequency and energy are directly proportional. Now, if wavelength and frequency are inversely proportional and they do this, when one goes up, the other goes down, then frequency and energy is like this. When frequency goes up, the energy goes up. When the frequency goes down, the energy goes down. Okay? So again, whereas wavelength and frequency are inversely related, energy and frequency are directly related. So, if you have a small frequency, there's a small amount of energy. If you have a large frequency, then you are receiving a larger amount of energy. Okay? So if you had two different waves, and the question was which one has a greater energy, you would simply ask which one has a greater frequency. Because the higher the frequency, the higher the energy. All right? A little bit of bobble, yes, no? We're good? Got that? Okay. So directly proportional, small frequency, small energy, large frequency, large energy. Now let's throw wavelength into that. If frequency and energy are directly proportional, and frequency and wavelength are inversely proportional, how does wavelength relate to energy? Well, large wavelength means small frequency, therefore small energy. And correspondingly, a small wavelength means large frequency, and therefore large energy. Okay. So the way to break it down when you're thinking in terms of energy, the higher the frequency, the higher the energy. The higher the frequency, the lower the wavelength. So therefore, the lower the wavelength, the higher the energy. Okay? If you remember, higher frequency is higher energy, and that lower wavelengths go with higher frequencies, it should be pretty simple to make the correlation. So if the question says, these two waves, here are their frequencies, which one has more energy? The answer is, the one with the higher frequency has more energy. If the question is, here are two waves, and they have these with different wavelengths, which one has higher energy? The lower wavelength has a higher energy, because the lower wavelength has a higher frequency, which has a higher energy. So, wavelength, frequency are inversely related. Frequency and energy are directly related. Therefore, wavelength and energy are inversely related. On the bottom of 105, it just says this in blue. It says, as a light wave's frequency increases, its energy increases. And as a light wave's frequency decreases, its energy decreases. And then on the next page, on 106, as a light wave's wavelength increases, its energy decreases. And as the wavelength decreases, the energy increases. Because a decreasing wavelength means an increasing frequency, and an increasing frequency means an increasing energy. And if we put that on the visible spectrum, you can see here, in terms of the wavelength, what I've tried to communicate here is lowercase unbold is small, capitalized bold is big, right? So as we're moving from a low frequency to a high frequency, low frequency to a high frequency, our energy is going from a low energy to a high energy, and our wavelength is going from a high wavelength to a low wavelength. Because these two, wavelength and frequency, are inversely proportional. That's why they get bigger in different directions. And frequency and energy are directly proportional. It means they get bigger in the same direction. Now, that's just generally speaking, how do we judge whether energy is increasing, decreasing, which one has more or less. But you know that's not good enough for chemistry, right? It's not good enough to say there's more. And then we get into the question, okay, but how much is it? So we have a formula for that. Energy is equal to Planck's constant times the frequency. H is the abbreviation for Planck's constant. It's named after Max Planck. He was a German physicist. And I'm not going to get into how he figured this out, but he determined that there was a constant number that you need. Kind of like the constant for the speed of light is always the same. In this case, H, Planck's constant, is always the same. And Planck's constant will be given to you. You won't have to memorize it, but you'll have to know how to use it. So energy is equal to Planck's constant times the frequency of the wave. Planck's constant is a multiple. Take the frequency, you multiply it by this number to get it into energy units. Think of Planck's constant as your conversion factor. You have something in the language of frequency, in hertz, and you need to convert it into the language of energy, which is joules. How do you do that? Planck's constant is your conversion factor to take you from the language of frequency to the language of energy, from hertz to joules. And it's 6.63 times 10 to the negative 34th joules per hertz. Again, accept it. There it is. It'll be given to you. Just know how to use it. All right? 6.63 times 10 to the negative 34th joules per hertz. So for every cycle per second, that wave is able to communicate 6.63 times 10 to the negative 34th joules. But remember, we're talking about frequencies that are huge. Multiple, many big exponential numbers. So that times 10 to the negative 34th, you know, it has to come into play too, because the numbers for the frequencies are so large as well. And we're going to do a couple of problems. Actually, we're going to look at example 3.3 starting on page 107. This work is all in your book, but I want to show it to you up on the board here and also be able to capture it for the slides for online. So we're going to take a look at these too. We ended a quarter after today, don't we? Yeah. So let's try to at least look at a little bit. Oh, this note too. A joule per hertz is known as a joule second. That's the unit. So how many joule seconds? That's the same as a joule per hertz. Remember, a hertz is a 1 per second. So it's a joule divided by a 1 per second, which is a second. Again, joule seconds, that's the units for Planck's constant. It's a joule per hertz. So example 3.3. They say a light wave has a frequency of 2.3 times 10 to the 16th hertz. What is its energy? E equals what? Given that frequency. Well, we just heard that energy is equal to Planck's constant times the frequency. The Planck's constant is a given, 6.63 times 10 to the negative 34th joules per hertz, times the frequency, which we were given, 2.3 times 10 to the 16th. So, estimating this number, again, before we go to the calculator, just looking at it, we got 6.5 times 2.5, 13, 14, 15, 16-ish, somewhere in there. 16, and we've got negative 34, positive 16, so we add those together, and we get a negative 18-ish. Okay? So 15 times 10 to the negative 18 is the same as 1.5 times 10 to the negative 17th. We were there. So how much energy does that wave have? Well, because it has a frequency of 2.3 times 10 to the 16th hertz, it has an energy of 1.5 times 10 to the negative 17th joules. And that's a unit of energy. That's how much energy that wave is communicating. Pick up with the second half tomorrow.